video, audio, focus, right, left, up and down. And so we start Bayes' theorem. Now, before we get too far into Bayes' theorem, we're going to draw pictures. I do like pictures. So let's draw a picture of the universe. And let's suppose that the universe is the disjoint union of some AIs. This dot means that AI intersect AJ is the empty set if I is not J. Now, that simply says that I can draw a reasonable picture. Don't know if it's actually possible to draw it this way, but our universe is decomposed into these A sub i's. Now, some people refer to this as a mutually exclusive partition of U. That's one way people will refer to it. Other people might call this a stratification of the universe. Some people refer to it as a disjoint dissection of the universe. But the most important thing is it creates the whole universe, and it's created by disjoint pieces. Now, if we pick some A, which lives inside of the universe, that did not work very well, so that one's got a little issue. Let's try this instead. There we go. Here's our A. What are these pieces right here that we're looking at? Well, the answer is all of those intersections are the following. That if we take A, we know it's the same as A intersect the universe. But that's the same as A intersect the disjoint union of the A sub i's. But that means that I can, using De Moivre's law, I can break this up into the disjoint union of the A intersect the A sub i's. And that's what these little pieces are. They are this piece right there. If this is AJ, then that piece is A intersect AJ. And they're all disjoint because the AIs are disjoint. All right, so we now have broken it up into lots of little pieces. Well, what am I going to do next? Well, what I'm going to do next is I'm going to calculate the probability of A. So the probability of A is the probability of the disjoint union of these A's intersect A sub i's. But since it's a disjoint union, the probability says we just add up over all of the i's. The probability of the A's intersect the A sub i's. Now, we happen to know what the probability of A intersect the A sub i's are because we have that intersection law. So this is the summation over i's of the probability of A sub I times the probability of A given A sub I. This is just a fact from what each one of those means from our definition of conditional probability. So now I'm going to go off to the side here and do something else. If the probability of A is positive, then what I can do is I can say that the probability of A times the probability of A sub k given A is the probability of A sub k intersect A, and I can divide and say the probability of A sub k given A is the probability of A sub k intersect A divided by the probability of A. This is another fact that comes out because of conditional probabilities. But I want you to notice that I intentionally put the A sub k's before the A's and they weren't there. So now notice that's what these things are being added up to be. So now what I can do is I can write down Bayes' theorem. Bayes' theorem says the probability of A sub k given A is the probability of A sub k times the probability of A given A sub k divided by the sum of the probability of A sub I times the probability of A given A sub I. So just putting those formulas together, we get this strange fact that some probabilities that are a conditional probability can be written in terms of the others. Now this looks complicated, but it's truly not, because first off, if you notice, you have the A sub k's here and you switch the order. And it looks like an intersection. It looks like a very simple calculation. And you divide by absolutely every other intersection in the bottom. So let's do an example of how this works. So first off, I'm going to write that theorem down. P of A sub k given A is the probability of A sub k times the probability of A given A sub k over the sum of the probabilities of A sub I times the probability of A given A sub I over all of the i's. This is the theorem that is called Bayes' theorem. And again, it requires the A sub i's to be a disjoint, another way of saying it is a disjoint cover of the universe. All right, so let's do an example. Let's say a factory makes springs. We have machine 1. It has a defect rate of 0.02 or 2%. We have machine 2, which has a defect rate of 0.01, 1%. We have machine 3, which has a defect rate of 0.03, which is 3%. So we have these machines that are producing in the factory, and one is better than the other. Now, one would think that it would be nice if we could run this one faster, make more, but anyway, use the machine 2 as much as is possible. Well, in reality, these machines have their own production rates, and let's just assume that machine 1's production rate is 35%, that machine 2's production rate is 25%. Oh, I should have been consistent. I was inconsistent. And machine 3's production rate, well, what's left? That's 60, so it's got to be making 40%. Bummer. The machine 3, which is the most defects, is actually making the most pieces. Now, let's write some obvious things down. So first off, let's just look at the probability of a defective spring. Well, it's the sum of the probabilities over the different machines. So what's the probability that it's defective on machine 1? What's the probability it's defective on machine 2? What's the probability it's defective on machine 3? But we have to include the conditions. So this is the probability of it being on machine 1 times the probability that's defective given it's machine 1, plus the probability it's on machine 2 times the probability that's defective on machine 2, plus the probability it's on machine 3 times the probability it's defective given it's machine 3. So this is not a crazy statement. Let's look at a tree here. Here, it says that 35% of the time it's made on machine 1, and then machine 1 either produces a defect or a non-defective part. If it's defective, it's 0.02. And so of reaching a defective right here is 0.35 times 0.02, which is exactly these two statements. And then there's also reaching machine 1, defective, and machine 2, and machine 2 is what, 0.25, and the defective rate of machine 2 is 0.01, and this to reach here is that one. So each of the defectives in these trees is one of these points. So clearly that's the probability of a defective spring. And we can calculate it, put it in, it's 0.35 times 0.02 plus 0.25 times 0.01 plus 0.4 times 0.03. And we get a number. I'm not going to worry about that. Now, I'm going to ask the following question. What is the probability that a defective spring came from machine 3? The probability that a defective probability that a defective spring came from machine 3, we're given that it's defective. Well, we can use Bayes' theorem. And Bayes' theorem says that we're interested in the defectiveness and we're interested in machine 3. So at the top, it will say the probability of machine 3 times the probability that it's defective given machine 3, because we reverse the direction. And in the bottom, it's the sum of all of the conditional probabilities times the probability of the machine. It's in fact this number. And now when we calculate that, it turns out we're going to get, 120 over 215. You can just plug these numbers in. Now, how in the world can we think of this formula? Well, one way to think of the formula is the restricted universe. If you look at the universe of where you know you have a defect, again, it's this part of the tree. These three probabilities add up to this number, but it's not adding up to 1. So what this is you're calculating, I have the probability came from machine 3 and that it was defective, and then I'm adjusting it to the world of a restricted universe. This is a normalization. Now, what's really neat about Bayes' theorem is that it actually talks about the reversing of givens. Now, that's non-trivial, because if you know something has happened and then you say it the other way, how do you know it can or could have happened the other way? So we often refer to A given A sub I, this probability, as the priors, something that you knew first. And then we refer to this as the posteriors, priors and posteriors. So how did that work in terms of the machine? Well, in terms of the machine, what we knew in prior was the defect rates and the production of the machines. And what did we figure out after the case? We figured out the probability that there were defects given a machine given a specific defects. Now, there's an entire area of what's called Bayesian statistics, and why, or Bayesian probability, and why do we talk about it this way? Because it requires us to know conditions on the probability. And in general, the empiricists just have data that's out there, and we don't know what model is actually describing it. But if you do these prior probabilities under some model, under assumption, then you can get these posterior probabilities that are based upon that assumption. A lot of people like that. And so there are actually two areas of statistics, the Bayesian statisticians and the empirical statisticians. We're going to head into the empirical, where we have a model, and then we're going to look at the empirical data that supports it, or claim that we understand that a model is there. We're not going to guess at what model might apply in a given situation. We're going to argue that we know which model it should be. Now, I want to do the last example in this section, which is a very powerful example. It applies to pap smears, and it also applies to the PSA tests for men on cancer. It is known that the probability that you will test negative, given that you have cancer, on a pap smear is 16%. So the pap smear for women that have cancer has a fairly high false negative. Now, the complement is the probability you test positive, given that you have cancer, is 84%. So that's the complement part. Now, let's look at the other side. The probability that you test positive, given that not cancer, is 19%. And that means the complement, the probability you test negative, given that you don't have cancer, is 81%. So here are some conditional probabilities. Now, once again, these need to be known in advance to do this calculation. These are the priors. And the amazing thing about it is test doesn't look terribly good. A lot of women don't have cancer but get a positive test. Very worrisome. A lot of women go in and they have cancer, they get a negative test. It seems that this test isn't great. But it gets worse than that. We're now going to do Bayes' theorem on this. So Bayes' theorem says, let's calculate the probability that you have cancer given you test positive. So I'm reversing these. Well, this means that I can apply the conditional probability, the probability of cancer and testing positive, over the probability of testing positive. And now we apply the formula from Bayes' theorem, and so we get 0.0. Oh, I need one more thing before I go on. I need to know in the United States the real incident rate of cancer. This is cervical cancer. So I need to know this. What is the probability that this is happening? So it turns out the probability of women having this type of cancer is 0.00008. It's a fairly low probability. Therefore, the not having cancer is a 0.99992. So this is a good thing. It's a good thing that doesn't happen very often. The test doesn't look great, but that's a good thing. I'm going to put these numbers in here. So now this is 0.00008 times 0.84. That's the probability of C, and that's the probability of testing positive given C. Reverse them. And then the strange all Bayesian portion in the bottom, 0.008 times 0.84 plus 0.099992 times 0.19. So there's the relative normalization, given that you've tested positive. Well, this number is equal to 0.00354. So this actually says that when you test positive, the probability of you have cancer is 354 out of 1 million people. So if every woman after a certain age is testing regularly a pap smear, and we're not using any screening process, we're not using anything to protect why we're doing it, we're just going to test everyone, there's a very, very, very small possibility when that test comes back that it says anything. One wonders if the cost of that is useful. But if it's you, or if the test is very cheap, then it's useful. There's an interesting publication, the book references it, whether or not this should be a common thing. In fact, for the men's side, it's even more clear. The men's PSA test, which tests for prostate cancer, turns out the incident rate is very, very low in young men, fairly high in older men. But then the problem about the cancer is it doesn't move very fast, and so most men outlive their cancer just from other causes. So it really is pretty non-useful to do a PSA test when you're young. It just doesn't catch anything. It's like 1 in 10 million people would be caught with a positive test. It's a pretty useless test for young men. But if you want to pay for the test because it's an insurance policy, it's very good. We've decided that because the cervical cancer strikes at a younger age, that this is a useful thing to insurance companies to cover, and it's a useful thing to use. And the law of large numbers came into play in terms of economics. Enough of these tests have been done that it's quite automatic, and we can check for abnormalities quite quickly. However, just because you get a positive back, this test says one need not immediately worry. There's many things that can be going on, just abnormalities, false positive, false negative, they occur. All right, there we go. That is Bayes' theorem.